Welcome to the workshop. I get a lot of questions about the tools I use to develop Apple II software and how to get started. While that varies a bit from project to project, I can take you through some of the tools that I use on a regular basis and show you how I connect them with a little custom scripting. I'll do that in the context of creating a small demo for the Apple II. So we'll discuss demo coding as well. This project is targeted to an Apple II with a 6.5 CO2 processor and with 128 kilobytes of memory. To put that in other terms, it should run on pretty much any enhanced Apple IIe, all Apple IIcs, and of course the Apple IIgs. Now I use these Apple IIs for final testing, and in particular to test accurate timing on real hardware. And I use the Windows machine behind me for some of the media applications that help me prepare my images and video content. But don't worry if you don't have all that. I do most of the programming just on a laptop with an emulator, and even though I'm targeting an 8-bit Apple II, I'll be using an Apple IIgs emulator. I'll show you why in a little bit. Before we get started, I want to thank everybody at OzKfest 2015. I wish I could be there in person. Perhaps next time. I've been wanting to contribute something to the OzKfest gathering, and around the time this one was announced, I had been working on two separate graphics and sound routines. I thought, why not put them together in a demo and present that for OzKfest? So here we are, and thanks a lot for motivating me to do this. For those of you not familiar with the demo scene, there are people who write programs just to show off what can be done with their computers. It's really a kind of art with a style of programming that typically focuses on a deep understanding of the hardware. Now, there are modern demos that use standard graphics and sound libraries like OpenGL and DirectX to do their presentation. But when you look at demos for 8 and 16-bit computers, they tend to rely on one or two types of effects: table effects or hardware tricks. Table-based effects is where you pre-compute a lot of lookup tables and use those to make things that would otherwise be impossible to do on low-powered computers, low-powered old machines. And these can include tables to do floating point routines or 3D vector lookups, but a lot more common ones are used for things like plasma effects, making a textured wormhole effect, or even just color mapping to various effect palettes. Hardware effects, on the other hand, use a lot of domain-specific knowledge. You might do things like push weird values into undocumented registers to get a screen to shift colors or pixel position. A lot of demos even use undocumented or even made-up video modes. And by made up, I mean they directly control the video hardware to create modes that allow mixing of features by rapidly switching up the video registers as the screen is being drawn. So this is what I'm talking about when I say it focuses on a deep understanding of the hardware. And when you do these kinds of hardware effects, you're not trying to write a program that can run on another kind of computer. It's really meant for that specific machine. And that is partly why they are so prevalent in demos. Demos are all about pushing a known set of hardware to its limits. And demo writing is different than writing a game or an application. Applications focus on data and allowing the user to do something with it. Games are essentially simulations where the user and computer interact in a real-time or turn-based engine. Demos typically run without user input and simply showing off effects. And I love demos, but I'm no pro at demo coding. So this is a simple effort, and I won't cover the actual programming in depth, but more the thought process and implementation steps. So let's take a look.
First, I have to explain low resolution mode. It's a graphical mode available as far back as the earliest Apple IIs. It was something Woz really wanted for games. It's 40 by 48 pixels with 16 colors, and you have the option of swapping the bottom 8 rows for 4 rows of text as seen here. This was an early game lemonade stand that used low resolution, which I remember playing in school. Even though the graphics were crude, the gameplay was really enhanced by having these visuals. What's really nice is accessing these features is extremely easy from AppleSoft Basic. You can set the color, draw horizontal and vertical lines, and plot points using pretty straightforward commands. For this demo, I'll be using double O resolution, which is 80 by 48 pixels, so that's twice as many along the X dimension, and they're actually square pixels now, whereas in low resolution, they're more of an elongated, fat pixel. I've used this mode before, most notably for Flappy Bird, and like Flappy Bird, we're going to have to do this project in assembly because we're going to need things to happen as fast as they can on the Apple II. But I need to back up and discuss low res a little bit more before we get into double low res. Here's a map of the 40-column display from the Apple IIgs technical reference. I apologize for the poor quality, but basically what it shows is the text display starts at address 400 in memory, and that would be for the first row of text at the top of the screen. And it goes up by 1 for each letter writing across, so other lines start at different addresses. So if you want to write to any address on the screen, you just need to know what line it's on, get that address, and then add the horizontal position. Great, that's the text display. What does that have to do with low-resolution graphics? Well, looking at another page of the technical reference for the low-resolution graphics display, you can see they share the exact same memory map. The only difference now is instead of representing a letter, each memory location represents 2 dots or pixels, an upper dot and a lower dot. The way this works is the byte is broken up into the 2 nibbles, with the first nibble or 4 bits representing the lower dot and the second nibble representing the higher dot. Okay, now that we all understand low res, let's take a look at double low res. Remember how I said the 40-column text mode had the same memory map as the low-res mode? That's important because similarly, the double low-res mode has the same memory map as the 80-column mode for the Apple II series. Double low resolution and 80-column text mode both work like their 40-column counterparts except for one catch. When you write to subsequent memory locations, it actually writes to every other column on the screen. What's happening here is you can only write to one text page at a time. Text page 1, which maps to main memory, is the odd columns on the screen. Text page 2 represents the even columns on the screen and is mapped to auxiliary memory. You can switch between main and auxiliary memory by using the text page 1 and text page 2 soft switches by either reading or writing to them. Although I typically use a store instruction to preserve the accumulator. So to me, this means there's kind of 2 main strategies you can use for updating the double low res screen. You can either try and update all of the information on the main page and then switch to the auxiliary page and update everything there. But the problem is, if you aren't doing that fast enough, then the user sees it half updated, and they get sort of a striping effect going up and down the screen, and it's not very pleasant. So a lot of the routines I do actually will go line by line, and it'll draw all of the main bytes for a line, and then all of the auxiliary bytes for a line, and then go to the next one. If you don't do it fast enough, then you'll still get sort of a tearing effect as with traditional sprite blitting, but it's not nearly as offensive to the eye, let's say. Now that we've kind of got an understanding of double low res, there's one last thing to bring up about the color palettes. It uses the same colors as the low res mode, and in fact the same color values when you're writing to main memory. But of course, just to complicate things a little, writing to aux memory uses a different palette. So have fun with that. So why does all this matter? I'll tell you why. If you want to write a video game or a computer demo, you need things to be fast. So let's say I want to draw a block of some picture data to the screen. If you store the pixel data linearly, you'd have to do a lot of work with index registers or something to skip every other byte as you're writing it out to main or auxiliary memory. The strategy I use is to take all of the double low res data that I have to input into my program, and before I do that, pass it through a script which will separate it out into main and auxiliary memory data blocks instead of one that has all of that data together. Additionally, the scripts handle translating the data that's going to be written to auxiliary memory to the different palette formats, so I don't have to worry about handling any of that myself. The side effect of writing your routines like this is that you're somewhat constrained into drawing your pixels at even boundaries on 2 by 2 borders. So if you wanted to move up a sprite or down a sprite by 1 pixel, you'd have to have pre-shifted sprites basically. And that's actually what I had to do for Flappy Bird. And not only that, I ended up writing many different routines for the pipes because they slide off the screen. So I had conditions for when they were on top, when they were on bottom, when they were being clipped on the left-hand side, when they were being clipped on the right-hand side, when they weren't being clipped. And then for each one of those, I had whether they were even or odd. So it can take a lot of work depending on what you want to put into your program. But we're not going to worry too much about that today because we're just going to be putting image data on the screen and not moving it around.
Now, I've been talking a lot about drawing your image data to the screen, but what I haven't brought up is how we generate our image data in the first place. And you could certainly go on your Apple II into double low res mode and start putting values into the screen memory and draw out your image that way and then somehow save that off to a file. But I'm actually going to use some things like animated GIFs or GIFs, whatever you want to call them today, and I'm going to run them through some software and some scripts that I have to generate our content, and I'll kind of show you how you do that in a semi-manual way. Now, I'm going to use Adobe Photoshop, which is paid software, but you can do this with free software, and I've also, in the past, I've had completely automated conversion systems using things like the command line tool ImageMagick. But for this one, for time constraints and just for quality control purposes, I'm doing it through Photoshop with a pretty tried and true technique that lets me manually tweak some things if I need to along the way. So let's take a look at that, how I'm going to actually get these images onto our Apple II program. We're looking at Photoshop here. I'm going to switch to a web browser and just did a search for some Apple II images. I like this one. I'll go ahead and copy this image. Go back to Photoshop. Let's put it in a new document. I'm going to make the canvas a little bigger so that it's kind of squared. Now I'll warn you right now that the aspect ratio is different on the double low res screen than it is on here, and if you're used to emulators you'd kind of know what I mean, where things kind of get stretched out a little bit horizontally on most emulators, the way they're presented on the modern displays. So I'll make the background the same color, and let's go ahead and change our image size just to make it easier, down to that 80 by 48, and I'm not even going to worry about the aspect ratio for this kind of quick and dirty demo. Okay, so now that is much smaller. Let me change one more thing. Let's go ahead and crop our canvas back down to 48 pixels. I don't need that dead space on the top and the bottom. Okay, so now we've got our logo, and I could just do a conversion down to the double low res colors, which are the same as the low res colors. I'm using the Save to Web feature here, which has a nice way to allow me to test some things out, but we'll go ahead and set an 8-bit ping format, PNG, sorry, and then I load a color table, which I already have saved. So this isn't perfect, but you get the general idea, right? I convert this data down to a PNG format that basically looks like double low res colors. And then what I do is I run this through a script that will generate the raw data in source code. So I can just put this into my code, already pre-separated into the main and aux RAM sort of data blocks, and use that in my code. So that's great. So another tool that I'm using here is Adobe After Effects, and it's another video sort of image processing tool, and does some animation effects, and I'm going to use it with this animated GIF. So you can see I've got a record spinning, and it looks pretty good, but when we shrink this down to 80 by 48 pixels, it's going to be hard to really tell what's going on. So to enhance that a little bit, the first thing I did was I put a little blackout over here and put a gray stripe that matches the double low res gray, so that as it spins you see that. And then I put an outline of an Apple logo there, so that and rotated that so it'll spin like that. and I put a little record hole, and I made it bigger than a real record hole because remember, it's going to be so small that might only be one single dot on the screen. And then finally I put a little gray blackout layer there because I don't want that to be dithered. I want it to just kind of be a solid gray so that you can still see it visually. So I made that, and then I exported this out into a series of frames that are in 80 by 48.
And here's what those frames look like. So far so good, right? My scripts support converting a ping image to raw data and exporting that as source that can be used in an assembly program. And at 80 by 48 pixels, remember there's 2 pixels per byte, an upper and a lower. That really works out to 80 times 24 bytes, or 1920 bytes. So almost 2K if I want to just store an image and then be able to copy it directly to the screen memory when I want to display it. That's okay if you only want to display 1 or 2 images, but we want to show a bunch of frames. So I ended up having to use some compression, and this type of compression is lossless compression, meaning we get exactly the data out of it that we compressed originally. I started with run length encoding, which is a very common scheme. You basically can use the high bit of a byte to indicate whether or not the rest of the number indicates the number of literal bytes that follows or the number of repeated bytes that follows. So when you have a lot of repeated data in your scene, this works really well. And we actually wouldn't be able to compress very well if our data was interleaved between aux and main memory. So this is another good reason to split it out, because you'll have longer runs, as they're called, for run length encoding if your data is somewhat normalized where it doesn't change as much. And this worked pretty well. I got up to about 50% compression on most of my images because there wasn't really a lot going on. But again, we want to have a lot of frames, so this wasn't really feasible for our entire set of images. So what I did is I kept the first frame as just a regular run length encoded image, and then for all of the subsequent frames, since there's not much change from the previous frame, I relied on what's called delta animation, where I only keep track of the bytes that change. And in this case, I was still doing run length encoding, but the runs indicated whether or not it had pixels that had changed or gaps where nothing had changed. And so when there's not a lot changing, it just compresses all those gaps down into basically nothing. And that's what we wanted. This is where I messed up big time. I decided that RLE compression wasn't good enough, so I needed to implement LZ4 compression. LZ4 is compact and very high speed and not too hard to implement on an 8-bit processor. Unfortunately, I had never done it before. I've used the LZ4 libraries provided by Brutal Deluxe for the 65C816, and they work great. This time I used the reference code by Peter Ferry, and it does work great, but I had a hard time getting it implemented. So just let that be a lesson to you that you really need to plan your resources, including your time budget, very well, or you'll end up being late like I am. Ultimately, I did get a little bit of compression gain, and I'm only using it for the keyframes right now, so it wasn't a huge win, and I ended up burning about 4 weeks trying to get that working. Now that I have it working, maybe in the future I'll use it for compressing the run length data as well, but there would have been some other issues with that. I would have had to have a more complex memory manager, and I obviously didn't have the time budget remaining for that, so oh well. I'm lucky to get it back to a working state, so now I'll show you what it looks like with the final sort of animation format for this demo. The movie starts with a pointer to the frames table, which holds all of the delta frames. The delta frames are pointers to first the main data, and then a pointer to the aux data for that frame, and then of course the pointer to the same for the next frame, and so on. Ultimately, it's terminated with a 0 word. The second part of the movie record is a pointer to the keyframe. And the keyframe itself is defined as a pointer to the end because I need that for my decompression routine. And then all of the data that's our compressed LZ4 data for that keyframe. The last part of the movie structure is a pointer to the unpack buffer where the keyframe will be uncompressed. And that can vary for each movie in case you want to have more than one of them sort of queued up and ready to go with their keyframes already uncompressed. Otherwise, you can reuse the same space over. Okay, so we've created an interesting system for some cool animations, but if you want to have a really interesting demo, it pretty much has to have sound. And on the Apple II, at least prior to the Apple II GS, By default, all you got was a 1-bit speaker that you could turn on and off, and you couldn't even really say on and off. You could just toggle it by toggling a soft switch for the speaker. And of course, all you could really generate were different square waves by varying the timing in between turning on and off the speaker. And that's pretty much where it ends for sound, unless of course you're a genius like Michael J. Mahone. Michael created a digital analog converter called DAC 522, and it's a 5-bit 22 kilohertz pulse width modulation wavetable synthesizer engine. Yeah, right? Like, who hasn't written one of those before? And I did get it integrated. Unfortunately, there were some things I couldn't do. Because it requires such precise timing, you can't really do animations unless you're somehow integrating it into a sound engine, which is really difficult. However, I could play short clips and kind of synchronize them with the video so that it would provide for some interesting effects. Ultimately, when I wanted to do a little bit of sound during other animations, I fell back to just some simple square wave generators that were easy to throw in there. So what's all this look like?